Hello mate, and welcome back to Let's Code Season 6. In the previous episodes we have done a lot of work getting some of our framework set up. Now we need to start looking at some of the more abstract concepts. And one of those concepts that we need to talk about is going to be pathfinding. Now the entities within our game, some of them will be NPC, some of them will be enemy mobs, some of them will be just maybe trash animals that don't really have any impact whatsoever, they just hop around the screen or whatever. We need those things to be able to get from point A to point B reasonably intelligently. It needs to be able to navigate around obstacles, and it needs to be able to navigate towards something important. For example, enemy mobs will need to be able to navigate towards the player. There's no necessarily any harm with them just moving randomly around the screen. And if you do want them to just hop randomly around the screen, then just feel free to ignore this video, this chapter in its entirety. But realistically, in any video game, you want your enemy mobs to be able to chase the player. So that's what we're going to achieve in this video. So in order to achieve this, the first thing we need to do is work with a class. Now we've created a class here called Node, and I will do a very quick description of how we're going to use this class and why it has the properties that it's going to use. In order for our pathfinding algorithm to output a route for our game objects to follow, what we need to do is create a daisy chain kind of effect where each node that we create has a reference to its parent. So think about it like stepping stones. If you're standing on stepping stone 1, then that stepping stone is the absolute parent. It hasn't got a parent stepping stone to it. But once you step onto the next stone, what we do is we write down the stone that you came from and the position of the stone that you're now standing on, and so on and so forth. And what this will enable us to do is, once we've found the best route, is to actually backtrack the positions of each node, then go to its parent, and so on and so forth, so that we end up with a route towards the object where we're going. So as you can see, our parent and our position are fairly self-explanatory. F, G and H require a little bit more thought. So F, G and H are basically values that enable us to calculate the difficulty or the value of each cell. Now what does the value actually reference to? So what we're trying to achieve is the cheapest possible route from point A to point B. And we use the calculations that we're going to input into F, G and H to determine whether one cell is better than the other for the route and what they are. F is the overall cost. That is the total of G and H. So F is just G plus H. G is the number of steps that we've already taken. So if we've taken 5 steps, G would equal 5, and so on, basically ad infinitum. H is the heuristic calculation for the distance to go to the object if there were no obstacles. So in the case of our algorithm, we don't allow diagonal movement, so it's going to be how many up and sideways or up, down, left and right side steps is it going to take for us to get to the destination, assuming that there were no obstacles there. So if it's 5 blocks up and 5 blocks across, then that would obviously be 10 steps required in total. So our total cost would be the number of steps we've taken plus the number of steps to go, and that will tell us the value of our node. Now the last bit is just our way of saying that if we use equals, if we compare this to another thing, then what we want to do is return true or false as to whether or not the position that we're on is the same as the position that we are comparing it to. So that's essentially all the class is doing, really. This is just kind of the basic building block that we're going to use in order to fill out our algorithm. Now that we've created our class, what we're going to do is we're actually going to use it in our function. Now this is the start of our A* function. Remember, this is not a function within the class, this is a function all on its own, so we make sure that the only thing that this is contained within is a Python block. And what we need to do is we need to input a matrix, a start position and an end position. Now the matrix is obviously going to be our room, the room that we're currently checking, the matrix of the room, so it'll be room.getMatrix. And Start and end are going to be the position where our thing currently is and where it's trying to get to. And as you can see here in my code annotation, it returns the path as a list of tuples and a list of positions that that object needs to go through in order to get where it wants to go. The next thing we need to do is we need to create a node for the start and the end positions to make sure that we've got references to those. And we're just going to set the G, F and H value for each one of those as 0 for the time being. There's no need to give those values of any real relevance because they're just markers that we're going to reference. Am I at the beginning or am I at the end? The next thing we want to do is create two lists. Think of these as bags. Every time we test a cell, we're going to put it in the closed list, and the open list is going to be where we put the cells that we have yet to check. That's all we're going to do with those two lists. And then, so what we're doing is we're going to take the start node and we're going to put it into our open list straight away, because obviously that needs to be checked. Now that we've got our open list with an object in it, we're going to loop through all the objects within our open list, our open bag. What we're going to do is we're going to create another node or reference to the current node, and at the moment that's going to be the first item in the open list. And we're also going to set its index as 0 because we're referencing open list index 0. So we're saying that current node and current index, these are just references to the object that we're looking at right at the start. Then what we're going to do is we're going to quickly whiz through the remainder of the stuff in the open list, and we're going to check, have I got the node with the lowest current F value? If I haven't, then I'm going to change my current node and my current index references to reference the item with the lowest F value. This just means that we're always working on the cheapest cell. Then what we're going to do is we're going to take the item that we've just found, we're going to take it out of the open list and we're going to put it into the closed list. The next thing we want to do is check, am I already talking to the node? Am I referencing the node that is the end node? If I am, then stage 1 of our check is complete, and what we then need to do is we need to create another list, which is going to be the list that we output from our function, and we're going to set our current another reference to the current node, and then all we're going to do is we're going to loop through all of the nodes one at a time, as in the ones in our daisy chain. We're going to say if current is not none. So if we haven't reached the end of our daisy chain, we're going to add the current position of the node that we're thinking of, that we're referencing, to our list. Then we're going to go from the current node to its parent, and we're going to repeat the process all the way back through the daisy chain, just adding the position of each cell into the path. And then this return path : -1 is basically just going to flip the list so that we're going from start to end, not end to start. Because if you remember, the order that we've calculated this in, we calculated it from start to end. So our references refer to each parent. So we need to flip the list backwards so that it actually returns it in the correct order. But that's all we're doing in this bit of code. We're looping through our daisy chain and putting the positions of each cell in our daisy chain into a list and then returning that to the user. Okay, so this piece of code, we're actually going to create another list called children, which is going to be a reference of the children of the cell that we're standing on. So we're standing on cell XY, and we want to be able to check all of the cells in all of the traversable directions. Now, because our game only allows up, down, left and right movement, we're going to say the position we're in plus 0x minus 1y, which would be the cell above us, then 0x and 1y, which would be the cell below us, then minus 1x and 0y, which would be the cell to the left, and then 1x and 0y, which would be the cell to the right. Okay, so those are the 4 positions that we're going to check referencing our original cell. So we're going to create a node position reference, which is going to be our current position plus the new position. And remember, we're looping through each one of these positions. So this will do this 4 times, and it'll create a node position that we can just reference shorthand rather than constantly referencing this mathematical formula of current node position plus new node position X, and then current node position, new node position Y. We're just going to create a reference to it. And now what we're going to do is we're going to say if node position, if the position of our node position is outside of the matrix, because remember that our matrix is a finite X and Y grid. So we're going to check that our node is actually within the grid by saying, is its Y position greater than the length of the matrix, or is its Y position less than 0? Or is its X position greater than the width of the matrix, or is our X position less than 0? Then we're going to skip this one because there's no point. So we're not going to do anything with this node that we've created or that we're referencing because it's outside the map. So there's no point in looking at it any further. The next thing we're going to check is it actually walkable? If you remember, our matrix is basically a grid of zeros. And then when there's an object there, it obviously puts the object instead of the 0 there. So all we're doing is checking, is the cell that we're looking at actually a value of 0? If it's not, then we'll skip it because the object that we're trying to move can't walk through that square. So we're not going to continue using that cell anymore either. If it gets through both of these two checks, then we'll add a new node called new node, and it will be a node based on the current node's parent. The current node will be its parent, and the position will be the node position that we created at the top of this loop. So we're creating a new node with the current node that we're standing on as its parent, and we're just adding its position in there. And then all we're going to do is add that to the list of children. So our children list will only contain nodes that are inside the map and walkable. Now what we're going to do in the last piece of code is we're going to loop through our children list, saying for each child node in the children list, we're going to check whether or not our child is already contained within the closed list. In other words, have we already checked this node? If we have, then we're just going to skip this one and move on to the next one. So if we haven't already checked it, what we're now going to do is calculate the G value, the H value, and the F value. So we're going to say current node's G is its parent node plus 1. Then we're going to say a child node's H value is the X position and the Y position difference between the place where we are and the place where we want to go. That's what that formula means. The star 2 just means modulus 2, just means rounds it up basically, because we need whole numbers. If it's an odd number, then we need to round that up. And then we're just going to say the F value is child node G plus child node H. So we're just going to add our G and H values together so that we can return an F value. And the F value, if you remember, is the total cost of this node. It's our way of comparing the nodes to see which one is the best one. Then we're going to check to see if our nodes are already in the open list. We need to make sure of that. So if the node is already in the open list, then we're going to skip it anyway. Otherwise, we're going to add this node to the open list in order for this whole algorithm to start again and can check this one if it's the lowest valued one. So that's all of our code. Members and patrons, that's channel members and patrons, will have the opportunity to download the code file for this project. But all of the code is contained within this video. You just have to piece the bits together and get it to do what you want it to do, okay? That's basically it, guys. That is an A-star pathfinding algorithm in a nutshell. You are going to have to go and use the pause function in order to copy the code if you're going to do that, and also to maybe you have to play it a couple of times to kind of wrap your head around what's going on. But essentially, it's that simple. It's not the most optimal way of figuring out a path from A to B. There are more complicated pathfinding algorithms that will find a more efficient route. But this is the simplest and the most appropriate for the style of game that we're creating. It just gets an entity from point A to point B. And it also is quick enough that we can do it every single turn for every single entity. So if the enemy mob is trying to navigate toward the player and the player moves, then it's not going to be hugely expensive for the enemy mob to recalculate its route every single second. So that's what we're aiming for. Anyway, thanks very much for watching that, guys. I hope you found it useful. Let me know what you think in the comments below, and I will see you again in the next one. But until then, you take damn good care of yourselves, alright? Bye-bye.